starting recording. We didn't miss so much. And it seems also based on what I heard in the radio that it's Teacher Day, interestingly. So yeah, Star Wars and Teacher Day, it's an interesting concept. Right, so I'm trying to see, thanks also Giovanni for letting me know about the recording. And just trying to see for more questions. So yes, lower score on the test and the green mission is being dropped automatically on CAT courses. It's an option on CAT courses. So as soon as, over all your grade, CAT courses identified your lower score and it's dropping it. So it's already done automatically. So, okay. All right, if you have any question at this point, you may just have to let me know by voice, okay? Because I will read a little bit less the chat. Otherwise, I'm getting distracted by that. So today we are talking about global warming, and I let you check this small video that you have on the top, which show you the temperature of cities. If I'm correct, it's, oh no, not cities, of countries. The temperature, the average countries, sorry, the average temperature per country every year. And it started the century ago and all over the 19th and 20th and 21st century. And observe it carefully. Okay, so what can you see? What could you be seeing from this small video? What happens to the temperature of the main countries being shown?
I see like a trend in 2017 where it just mainly stayed above 10 degrees Celsius. There was really no drop but below 0 degrees.
Yes, exactly. We have an increase of temperature. Temperature becomes hotter and hotter. If we go back in time, most of the temperature, you could see some orange, but you could see some blue happening, meaning that we were below the average temperature, -1 degree Celsius, most of the 20th century. But by the 90s, we're starting seeing definitely more oranges happening. And so since then, we have an increase of temperature that is becoming bigger and bigger. And from orange, light orange, we are even now in red. So that means that everywhere in the world, we tend to observe now an increase of temperature. So this global warming has many ways we can show you that it's really happening. I know that there is some lobbyists behind some other interests saying that global warming is not happening. We have so many different records and so many observations on the planet proving, in fact, unfortunately, that there is an increase in temperature. And so it's not about how can we solve it. We are already past the point of return in some way. So mostly it's how can we mitigate? So how can we reduce the possible impact of global warming, and how can we adapt to the change that are already happening? So again, the idea of solving global warming, this is over. Okay, we have done already too much damage since the 2 centuries ago for this kind of situation to go back to the way it was. So we just have to be able to mitigate, again, kind of modifying our habits to possibly reduce the consequences of global warming and finding ways to adapt to those changes. So in some way, mitigating is for us, for our generations to come, to not suffer too much, but also for the planet, for the biodiversity, for our resources to not be under stress and adapting definitely to possibly in some way getting used to live in warmer climate and to deal with those situations, but also adapting our way of living to also reduce the possible impact. So today we will be talking about climate and the climate change. And then on Thursday for the last class, we will be talking about really global warming. So see, I'm changing from climate to global warming. Those are not, I would not say two different, extremely different things, but they have to be differentiated. And I will come into those differences by the end of the lecture today. And we will talk about mitigation tactics, and what we can do to possibly reduce the impact of this global warming that is happening now. So first, we'll look at what is climate and how climate is working. And so first, I have a quick discussion question for you. Is we are speaking about climate, but how is climate different from weather?
Weather is just like the day-to-day temperature of an area, but climate is like the overall like weather over a long period of time, and so like
Yes,
it can gradually increase and decrease or whatnot.
exactly. So correct point on that. Climate is another. I mean, it's the state of the atmosphere over a very long time, and usually we can look at climate mostly over a small region, a city, for example, or maybe a county. You can look at the climate over California, and you can look at global climate over the planet. Weather will be mostly more localized, so it will be usually by cities or small areas, and it will reflect the state of the atmosphere, but during the day or during half a day, for example. And so we tend to have different kind of information between the fact that you're observing and you're measuring weather, or you're observing and measuring climate. Okay, so let's take a quick example of weather. We just said weather is really local, localities, condition of the atmosphere. So we're looking mostly in the time of, in the range of time, we're looking in terms of an hour, of the hours or day. And mostly you will have information such as the true value of the temperature, for example, lowest temperature in the morning, highest temperature in the afternoon. That can go with some example. You can see 42 degrees Fahrenheit, 102 degrees Fahrenheit. You will have indication about the possible amount of rain that you will receive over the day, maybe a 40% chance of rain, and an estimate of maybe 2 inches of rain falling during this precipitation event. And then you will also have information regarding wind speed, wind direction, the type of clouds you will observe, if your sky will be with clouds or not, humidity, all of those. So this is in fact really short-term condition, as I see Maricela exactly, when climate looks over a longer period of time. And in general, on the literature, climate is estimated is kind of averaging about 30 years of observation. So we start speaking about climate when we observe the trends over a period of 30 years, more or less, of observation. And then, based on what we observe on the planet, we can simplify, for example, the type of climate we observe on the planet by separating into specific climatic regions, such as, for example, polar climate or tundra. We can talk about tropical climate. We can talk about temperate deciduous forest climate. We can talk about grasslands, such as right here in the Central Valley. So we can simplify a little bit. But if you go into smaller scale, such as looking at the state of California, you can even identify different type of climate within California. The climate we have in Central Valley is slightly different than the one we have in Southern California, for example, and it's quite different from the one we observe along the coast, especially around the Bay Area, more or less, or for example, in the Sierra Nevada. So we can definitely establish some differentiation based on the scale you're looking at this, this type of information. So the question is how, I mean, in terms of weather, I would say, where is weather coming from? I would invite you to join ESS 15. That would be probably, that should be taught next spring, next year. But for now, we are just focusing on climate. So the weather, we'll set it apart. And we're looking at why the planet Earth has different climates. So let's look first at a quick video explaining you the Earth energy balance and how it works.
The sun pumps out energy in all directions, 24/7, and Earth soaks in it every day. Some of that energy gets absorbed by the oceans, the land, the atmosphere, and some gets reflected back out into space. How much stays and how much goes is a function of Earth's energy budget. Almost all of Earth's energy comes from the sun. As sunlight heats the planet changes. The most obvious transformations are with water. Oceans soak up heat, warming the planet, but warming water evaporates, which forms clouds. Those clouds, in turn, reflect sunlight back into space, which cools the planet. When the clouds dissipate, sunlight once again warms the water below, and the cycle continues. Other areas of the world have similar cycles. Polar ice caps, for example, reflect sunlight, while dark land surfaces soak it up. Overall, the amount of energy leaving the planet is equal to the amounts coming in, and Earth's energy budget stays roughly in balance. And it's a delicate balance. That's why NASA has missions designed to keep track of how much energy the sun is putting out, as well as missions designed to keep track of forces on Earth that might alter how much heat the planet traps. That energy balance isn't simply a scientific measurement, but a description of one of the most fundamental conditions for making our planet conducive to sustaining life.
Okay, let's see, upright. So the video was going into maybe more details already regarding the interaction between the sunlight and the water. But we can go into a more basic idea really regarding looking at the interaction between the planet Earth and the sun in itself. And so if we're looking at the interaction based on the energy, we are talking about what the way we call it is a solar radiation energy balance. So it's looking at balance between the energy received by the sun and the possible energy released by the planet. So we start with the beginning. We have the sun at the center of our solar system, and the sun is emitting all the time a specific amount of energy. This amount of energy is quantified based on a surface, and so you have the quantification, which is in fact 342 watts per square meter, and but thus, I would say this number, you don't have to remember, okay, I just place it for information, just to say that over time, at least right now, this is the amount of energy that is constantly received on the planet by the sun. And the way that we are receiving this energy is mainly through a wavelength that is the visible wavelength. This is why we are species, we are in the organism that have our sight based on visible, because in fact we're using the light of sunlight to observe, to see what's happening around us. So that's why we, human and other species, we have developed a sight based on visible, because in fact we are using the main source of light coming from the sunlight. And so this emission of light coming from the sun reaches the surface of the Earth, and it's being absorbing at the surface of the planet. But what would happen in case there was, we would stop, let's imagine that we are stopping the balance right here. So the sun emitting its sunlight, the planet is just absorbing the sunlight, and we stop that. What would happen to the planet? overheat, okay, the planet will definitely warm up more. And at some point, you know, you will reach temperature that possibly will go into melting or maybe imploding. Who knows what could be the consequence of this. And of course, this is not stable. So at this point, the planet by itself will, to be in equilibrium, the planet will release some energy too. So the planet, as we can see, it's emitting also its own energy. But our planet is definitely having less energy than the sun. The sun is just big nuclear energy happening all the time, emitting a huge amount of energy in the visible. Our planet has lower energy. And so the wavelengths, the energy type being sent by our planet is of a higher wavelength. So it's in fact the infrared, which has quite less energy in itself. And it's this emission of energy is just to make sure that it's balanced, okay? The idea that you're not overheating the planet by doing this. What we can see also from this figure that I'm showing you right here is that there is more energy happening at the center, not the center, sorry, at the equator of the planet than at the poles. You see that if I want to look at quickly the energy I'm receiving right here, if I'm looking at the pole, the same amount of energy will be shared over a bigger surface, which means that if you have to divide the energy by the surface, you have quite less energy at the poles than at the equator. And so indirectly, the energy is being transferred from the equator toward the pole. It's not a perfect system, but this transfer of energy from the equator to the poles is in fact explaining why we tend to observe different climate on the planet, going from tropical climate to polar climate at the poles, okay? I'm seeing a question about, is it possible to see more precipitation? I suppose that was coming with the question if the planet would not emit, its own energy. I would suppose that if the planet was not emitting its energy and only the sun would just warm up the surface, all the water would have just evaporate and it will not have precipitate. No condensation would have happened. And in fact, our planet would just be a dry planet. Like, for example, Mercury. Mercury is pretty dry. Nothing happens to it. So if we look at this schematic and just looking at this balance, what we found is that the planet, the temperature of the planet should be below freezing. In fact, without something that we call greenhouse gases that we will just talk in a bit, the planet would be about 33 degrees Celsius cooler than it is. So that means below freezing point, meaning that all the planet should be frozen. But we have gases happening on the atmosphere that allow us to have a planet that is above the freezing point. And if we are interested, if we tend to be curious, we can look at what happened in the other planets. And I will show you the pole in just a little bit. But we can see that from that, for example, the Earth right here has a slightly positive value as for the temperature. Mars is negative. Venus is quite warmer. It has a strong positive value. And Mercury is also positive value. What would be, if you were looking, so imagine your sun, maybe let me place red. So this is, right here, this is the sun, okay? Based on the graph, what would be the trend that you could describe? Maybe I would say, do not look at Venus, okay? For the trend, it's easier to look at Venus. What would be the possible trend, the possible hypothesis that you could be reaching by just looking at this graph? So you're looking at the information that you have in the graph is the average temperature, and we have positive values and negative values. And on the x-axis, you have the distance of each planet from the sun. So what can you be seeing from this graph? the temperature decrease, you have to be really more, no, I wouldn't say specific, but finish up your sentence, Isabella. How, you know, the temperature decrease when what? Is it over time? Is it based on something?
Professor, I would say that like
Yes.
the further, I mean, yeah, minus Venus, the further away you got from the sun, the cooler the planet was, or like the lower the
Yes.
average temperatures were in Celsius.
Yes, Matthew, exactly. And you're joining Peyton, who made the same observation. And I suppose Isabella was making the same observation. She was just missing the second part of that explanation. But as further away you move from the sun, of course, the cooler your temperature become, which is in fact something logical. Right now, we tend to be coming into summertime, but remember a couple of months ago when it was really cold outside, and maybe you had a heater outside, you were maybe eating outside of a restaurant, I know that it was possible to happen. You definitely want to be close to the heater, because the further away you are, the colder you will be. And that's exactly the same idea. So beside Venus, this is in fact the trend. And we can almost draw, I mean, I wouldn't be perfect on drawing this line, but a line that shows you kind of almost a linear relationship between temperature and distance. However, Venus is not the same. So why do you think Venus tends to be an exception? And I'm providing you a few answers for that. So it should be an easy question, mostly, especially if you read carefully the slide. All right, we have 76% of you voted. I'm giving 15 more seconds to cut the final vote. That's the only polling of the day, by the way. I won't have any other questions or any other poll for the rest of the session. So 5, 4, 3, 2, 1, closing the poll. So majority of you mostly go at 33% because it's closer to the sun. But if it's closer to the sun, we found another planet that's even closer to us, which is Mercury. And if I follow your idea, well, then Mercury temperature should be something like that. But it's not the case. So your first question, I mean, it's closer to the sun, is not okay. I mean, the temperature of Venus, yes, it is closer to the sun than the Earth, but Venus is even closer and the temperature is less, okay? So it's not possible. Then the planet produce more internal heat. That could be a possibility, but in some way, this is definitely harder to measure. And if you come with this point, then we can also take as a reference Mercury, which is a dead planet. Nothing happened. Mercury is just a big piece of rock orbiting around the sun, and there is no internal heat. So definitely that would be the heat can be produced by Venus, but because you're in space, the heat should be lost. So it doesn't really correspond to that, because you're producing heat, but the heat should be lost. So definitely you come into the third point where there is something with the atmosphere. It may produce internal heat, but you need an atmosphere to keep that heat to not be lost in space. And definitely the atmosphere of Venus is very thick of greenhouse gases. It's very thick of those specific gas that tend to like heat and trap the heat in itself. Okay, So exactly, Dylan, I'm seeing what you're mentioning, so, and also what Maricela was mentioning. It's because of the greenhouse gases and the thick atmosphere of Venus that it tend to keep so much of the heat inside of the planet. In terms of the number 4, it's not the smallest rocky planet. The smallest rocky planet again is Mercury, and then I think, in fact, to be honest, it's the biggest rocky planet. This one I don't remember. I will not tell you anymore. I don't remember if Venus or Earth is bigger, to be honest. But in a way, it doesn't impact on the temperature of Venus in itself. Then Alisa, you're asking me another tricky question, to me at least, I would say. For Venus having volcanoes, I do not know personally. I don't know. I have a little bit more information on Mars itself, but I don't know about volcanic activity. Mars had volcanic activities. It's, I suppose, quite possible that Venus also had in the past. I'm not sure if it's still happening nowadays. I don't know about this. I don't remember if Venus is still an active planet or not regarding its nucleus. But that's a good question to be looking, in fact. So if anyone wants, for sure, you can reply to that question. And thanks, Dylan, to provide information regarding the size. Thanks. I didn't remember exactly. So what happened with these greenhouse gases? Let's look quickly at this video for an explanation of, and then I'm coming into a quick summary. So let's see. Well, I can play all the video and then I play it back for you. All right, so let's play it back again. The first thing happening to look at the greenhouse effect on the planet is the fact that the sunlight coming from the sun, visible radiation comes into the surface of the planet, okay? And so we have this energy is what we call a short length solar radiation, just it's a higher energy at this point. And then my word is a little bit tricky, in fact, because I should maybe mention that this energy of the sun is being absorbed by the planet, okay? The planet takes into it this energy. It's not that it's reflecting by the energy of the sun. Instead, the planet will emit this infrared radiation that goes into space. But those gases, so you have the emission of the planet going to space, but those gases are trapping those infrared radiation. And by trapping the infrared radiation, they warm up and they in fact increase the temperature of the atmosphere. Okay, so let me just correct directly. So please take note, okay, you have, I should say, the energy of the sun, okay, so that's a visible energy. This is absorbed, okay, so I would say absorbed by the planet, by Earth. And then as a consequence, the planet, of course, has to make a balance. So it's emitting infrared radiation, okay? And that's just part of the balance. But part of this infrared radiation is being trapped by the greenhouse gases. You have greenhouse, let's see, greenhouse gases, okay? And part of this energy is just being trapped with these greenhouse gases. And this is what's warming up the planet, okay? As a consequence, the temperature is increasing, okay? So that was something maybe to correct on this slide, because in general, this is kind of the popular idea that the Earth taking some of the solar light, but it's reflecting back, and that's a solar light that is increasing the temperature of the planet. It's not true. It's not the temperature, it's not the light of the sun that's warming up the planet. It's in fact the emission of the Earth through its infrared that is warming up indirectly the temperature of the planet. Okay. So So I see a question about from Juan about those gases, those greenhouse gases possibly escaping the atmosphere. They do not escape the atmosphere because in fact the atmosphere, that is the layer that we observe all around here, this is an atmosphere that is maintained close to the surface because of gravity. Okay, so gravity makes sure that all the gases, all the material on the planet stay close to the surface. So those gases are not escaping space. Okay, we have very little amount of material escaping, in fact, our planet, because gravity is a strong pulling to the surface. So speaking about greenhouse gases, what are greenhouse gases? Can you tell me one type? Cite me one greenhouse gas you may know. We have at least one or two famous ones. Methane, it's a correct one. CO2 is another correct one. And NOx, no, NOx is not a greenhouse gas. So methane, CO2, there is one that is, I would say, almost a basic element that you know, and in fact, I think it's probably the compound or the gas that you know the formula first. When you start learning chemical formulas, it's probably the first one you start knowing, or the second one. So ozone is a tricky one in terms of greenhouse gases. And René, yes, René, you're correct. H2O, water, okay? Water vapor is in fact a very strong greenhouse gases, a very strong greenhouse gas, which is part of a natural cycle. That is why we tend to not look too much at water vapor in terms of greenhouse gas, because it's already included in the system. We as humans tend to not emit more greenhouse gas. So we tend to not emit more water vapor than before we were there. So water vapor would be the first one, then carbon dioxide, methane, nitrogen oxide. So in fact, that would be in fact correct, Esther. I should correct that. This is a mistake on my slide. This is not nitrogen oxide, but it's nitrous oxide. That is should be considered. Okay, so nitrous oxide, not nitrogen oxide, and what we call the CFCs, chlorofluorocarbons, which are in fact gases that we use a lot. We use them a lot in fridge, ACs, in all the cooling system that we are using in our society. And we can see that the majority, if we look at the gas of our atmosphere, water vapor is definitely having the strongest, I mean, it's a greenhouse gases with a stronger concentration on the atmosphere. Followed then by carbon dioxide, by methane. Ozone, kind of a tricky one, definitely. I'm not venturing myself too much into ozone, and then CFCs and others. And what we can see from this graph is not all the greenhouse gas tend to have the same behavior. Some greenhouse gas will have the potential to warm up more the atmosphere than the other. And so we just to scale it, it's like making the temperature, you have to scale it to something. So we have scaled the potential to warm up the atmosphere based on CO2, carbon dioxide. And so carbon dioxide has a value of 1. So we compare everything to carbon dioxide. But for example, a molecule of methane will warm up the atmosphere 20 times stronger than CO2. So good news is in the atmosphere, we have more CO2 than we have methane. But you had one more molecule of methane, that is the equivalent of warming up the atmosphere of 25 molecules of CO2. Okay, so indirectly, if I'm looking at the, how would you say, the heating capacity, maybe if you want to call it this way, heating capacity, my handwriting is so bad. So one molecule of methane would be equivalent to 25 molecules of CO2. So definitely, if you have to choose, you would prefer to send into the atmosphere CO2 molecule than a methane. And if you look at nitrous oxide or CFCs, those are even stronger in terms of their capacity of forming up the atmosphere. Luckily, we have less of them too. Okay, so we see that most of the greenhouse gas we tend to have in the atmosphere is mostly CO2. And we observe their concentration changing over time. You have from specific records, we will talk in just a little bit. Let me clean up my handwriting right here. But over the last almost million years, over the last 800,000 years, we have observed changes in the CO2 concentration, as you can see right here, and changing in the methane concentration right here, which are directly linked to changes in temperatures. In fact, if you look carefully at the graph, there is a pretty good correlation between the temperature we measure on the planet and the concentration of those greenhouse gases. When there is an increase of greenhouse gases, methane or CO2, there is an increase of temperature. When there is a decrease of them, there is a decrease in temperature. So there is a strong relationship happening between those greenhouse gases and temperature, showing us that definitely the Earth's temperature is driven a lot, of course, first by the sun, by the sunlight, but then by the amount of greenhouse gases we have in our atmosphere. And now, the next part of the session, I'd like to check with you how we were able to get those measurements. Because right now we're living in prison. How are we able to have this temperature coming back almost 1 million years ago? How can we be able to have information regarding the time of the dinosaurs? All of this information. So let's look at climate change, what's causing the climate change, but first, how do we know about those type of information? How do we get an idea of those records of temperature in the past? Before I'm asking you the question that you're already showing, that should have been shown after, we have, of course, nowadays, we're making direct measurement of temperature of the gas concentration. We make temperature of a lot of things, and we do it on land, we do it at the mountains, we're doing above the sea. We even use satellites now to make this type of measurements everywhere on the planet. This is for now, but we have to also be aware about what happened in the past. For that, we created a science that is what we call paleoclimatology, which studies the past information of the climate based on some specific tools. Those tools is what we call climate imprints or proxies. And usually those proxies, those climate proxies, we have to turn into geology to have an idea of those type of proxies. And the time scale will be different. Some of those proxies will provide us ideas about what the climate that was there maybe a couple of thousand years ago. Some others will provide you information about a couple of million years ago. And so how can we know about this past climate change? This is in fact the question I have for you. Which tools do you think we are using to have an idea of the temperature in the past or the climate in the past? Which tools do you think we are using? Hopefully, I'm hoping that with this question, you're not looking at the handout and the slide after, because of course it's an introduction for the slide after. Fossil record, definitely. In fact, this is one that I need to add into my list. I didn't place it, but definitely fossil record helps you getting information about climates. Ice cores, exactly, Kiana. We can use ice cores to get information on the past climates. Sensors of gases, but Emmanuel, this only works now when we have, the technology, but before human existed, we didn't have sensors for gases. Measure water levels, this is also something that works now, but how do you get this type of information in the past? So imagine you're a young researcher in science, and we ask you to look for information in the past, temperatures. What would you maybe look at? What kind of tools do you think you may turn to have an idea. Let's say I'd like to know the temperature of the planet to know if it was warmer or cooler than now, maybe 2 million years ago. How do you know about that? You may turn into rocks. That's not an easy job, but you'll have to look at the formation of rocks at that time. So possibilities, but definitely not the easiest one. You have to be a very pointy geologist to know about that. Because usually rocks will tell you more about its environment of deposition. The type of, if you were in a river, if you were in a lake, if you are exposed to the wind, stuff like that. You may be using plants or some soil, definitely, to have those type of idea. Let's see if trees sounds like a good plan. With my example, of course, trees will not work because trees do not last for 2 million years, but we can use trees for information in the past, maybe not that long as million years. So let's look at, I think you kind of already cited most of the example we could find. We could look at, as Maricela said, we could use as looking at soil sample. In fact, this is what we call sediment cores. Most of these sediment cores, you go into a lake and you drill into the soil of your lake. Or even, sorry, you also say sediment. I missed that. So you were correct too then in this case. You also can do it in a shallow ocean, which you need a boat for that. And the idea is that you are drilling and extracting a portion of the soil. And you're looking at the information that can be the type of soil that you are observing, the type, whether it can be sandy, can be clay. This will give you an indication of the depth of the ocean or of the lake. You can look at the different type of organic material which refer to the fossils. So you will be looking if you find plants, if you find pollens, and this will give you an indication of the climate in the past. Speaking about pollen will come just in a bit. There is one that I'm speaking now, I won't spend too much time on this, is what we call stable isotopes. Mostly this is definitely a more pointy chemical study to do. Mostly it's related to oxygen, and especially the oxygen that is contained in water, H2O. We know that when it's very warm, what happens is there is a lot of evaporation of water from the ocean. And so when there is a lot of evaporation of water from the ocean, there is more heavy oxygen in the ocean than in the atmosphere. And if we are in a cooler period, there is more light isotopes, so heavy oxygen in the ocean than in the atmosphere. So we're looking at the ratio between, so I forgot to mention, isotopes are the same element, so in this case oxygen, but they have a different, within the oxygen, if you look at the nucleus, they have, it can be that a few of them will have an extra neutrons in the nucleus. So some of this oxygen will be a little bit heavier than others. And we are looking at this difference of size of, I should say, of weight. And so the ratio between heavy oxygen and the light oxygen give you indication about temperature. So I will just stay with that. Based on the ratio between heavy oxygen and light oxygen, we have an indication of the temperature, okay? It tends to be a very tricky science that needs, of course, more than just 5 minutes in the class really to explain. So then after we have the pollens. The pollens can be found in the cores, in the sediment cores, and definitely the pollens, well, each type of pollen that you can see in this figure belong to a specific plant, and each plant will grow under a specific type of climate. So if you're able to identify the pollen and identify the plants, you can have an idea of the type of precipitation, the type of temperature. We can also use coral reefs. Coral reefs are like almost kind of forest under sea, and so we have an idea of coral reef will usually be established in very warm environment and shallow water, and so any fossils of coral reef will give us an indication of specific temperature of water and depth of water at that time. Juan was mentioning about tree rings. We can look at cut down the trees. And for the past hundreds of thousands of years, for some trees, we are able to look at the rings of those trees and the space between each ring, which is being created every new year. The space between each tree indicates you the type of temperature and precipitation that you can observe at that site. And finally, ice cores. Ice cores are great tools to look at the past because they contain a lot of gases, they contain a lot of dust, they may contain pollens. They are also a way to record, I mean, beside the gas, they're also a way to record the temperature at the time when they form. So ice cores have become really good. The only issue about ice cores is we don't go older than 1 million years. In fact, the oldest one being studied has gone into this 800,000 years with the graph I showed you before. But with all of this information, we were able to reconstruct the climate of the planet since it kind of existed. And what we can see is on this graph, right here, okay, warmer than present, cooler than present, we see that most of the Earth's history was mostly in a warmer type of temperature than nowadays. We have a few exceptions, like if you look at around 750 to 500 million years ago, around this time right here, okay? Oh, sorry, maybe I should. Right there, we have what we call the possible snowball Earth. At that time we have some proxies showing us that maybe all the Earth was recovered in snow and ice. And so based on some change of orbits, it went out from that. But definitely a possible time that the Earth was definitely covered by snow and ice. Then we observe around 215 million years, a dramatic warming up of the temperature, which coincides pretty well with the development of the dinosaurs. Dinosaurs definitely were species adapted to warm temperature because they were cold-blooded. And then after, we can see that after the extinction of the dinosaurs, the temperature slightly, little by little, went down. And we had a nice decrease of the temperature being observed over the last 65 million years, more or less, which would have been tougher for the dinosaurs to survive. And if we look at 1 million years ago, the temperature was definitely cooler. We're starting at that time entering into those type of phases where we had glacial period, interglacial period, where we had very cold time period and very warm time period. And definitely, it doesn't seem to be, but a small degrees definitely make a difference. So let me just explain you how all of those changes were possible to happen. So most of those changing happen through, I would say, three to four parameters. The first one were the distribution of the continent on the planet. We know that the continent have been moving. This is what we call the tectonic plates. And these tectonic plates being illustrated here is induced by some motion of the magma below our feet during kind of subduction zone, conversion region zone, all of these geologic features you may have heard. But if we look at in the past, our planet has changed through time because the continents were moving. And I have this short movie showing you, oops, sorry, I went too quick. This short movie shows you the motion of those continents over time. If it wants to play, come on. There's nothing happening, and I checked it before class, so. All right, well, I'll place it back on CAT courses, but sorry for that. The movie was working fine before class. Who knows what's going on? So, well, anyway, the tectonic plates definitely is kind of impacting on the climate because we know that if you have more land in a place, it will warm up faster than if you have more sea. And right now we have more land on the northern hemisphere, which explains why the global warming happened more in the northern hemisphere than in the southern one. Then we have volcanism also tend to be a cause of possible change in temperature because over time, those volcanic eruptions, especially if we have lots of volcanic eruptions, this can impact on the climate by reflecting sunlight and so prohibiting the sun to reach the surface. If there is the sun reaching the surface, there is less infrared emission being emitted, and so there is a cooling down in temperature. And definitely we can observe a drop in temperature every time there is a volcanic eruption that is being part of this record right there. So volcanism usually associated with the cooling of the temperature. Then we have some specific orbital thing that happen between orbital changes happening between the Earth and the Sun in itself. We have 3 cycles that play on what we call the eccentricity, the axial tilt, and precession. Those are all different types of changes happening with the orbits of the Earth around the Sun. And for that, I'll show you this movie that definitely explains it better than what I could do with my head right now.
Most of us have heard of the ice ages from movies.
Everybody down!
20,000 years ago, places like New York City were covered in ice. But that wasn't the only time. There were a bunch of ice ages, going back millions of years. And here's the crazy part. By looking at cores of mud from the bottom of the ocean, we can tell that these ice ages actually came and went on a schedule, like clockwork. In fact, the entire world got hotter and colder with the ice ages. So what caused these huge swings in Earth's climate? Actually, it was clockwork, corresponding to slight shifts in Earth's orbit, now called Milankovitch cycles after the Serbian scientist who started to figure this out. We know that the gravitational pull of the sun, moon, and other planets makes the Earth's axis wobble like a top on a cycle of about 20,000 years. The tilt of the Earth also shifts about every 40,000 years. And the shape of Earth's orbit around the sun goes from more circular to more like an oval on a schedule of about 100,000 years. All of these changes affect how heat from the sun warms the northern hemisphere where ice sheets can grow. So, the same types of planetary movements that create our days, weeks, and years actually seem to also create something like superseasons, our climate. But that's only part of the story. Because with the orbital cycles, when the northern hemisphere warms, the whole planet warms. And when the northern hemisphere cools, the whole planet cools.
All right. So that was at least giving you an indication of how the planets orbiting around the sun tend to impact. And so all of those 3 parameters, which are tectonic plate, volcanism, and those Milankovitch cycle, or if you prefer orbital cycles, have naturally played on the climate, explaining why sometimes the climate was warmer than sometimes the climate was cooling down, okay? Another parameter that I do not mention now, but well, it's mentioned now, but more for a human reason, but it's also the greenhouse gases. We saw that greenhouse gases are natural gases happening on the planet, and those gases have been emitted at different type of rate with different concentration, and they're also participating in the warming or cooling down of the planets. However, at this point, with what we call global warming, so we're moving from a climate change, which is natural, to a global warming, which is in fact the current climate change being induced by human. What happened is we are not playing on volcanism. There is no more volcanism than usual. We are not playing on the orbital effect because we are not able to change that. We are not playing on the tectonic plates neither. Humans are not able to do that. But humans are playing right into the concentration of greenhouse gases, especially with the burning of fossil fuel. And if we look at the increase of CO2 over the last 100 years, it moved from 300 ppm to 400 ppm. Don't worry with the units. It's just about a third of the increase. The resulting part is with this third of increase of CO2 emission, of CO2 concentration, the temperature of the planet increased by 1 degree Celsius. That's a really big deal because I show you, a graph where we could observe that the temperature of the planet was warmer than today and was fine. At the time of the dinosaurs, the planet was definitely warmer than today. So definitely, we have tons and tons of newspaper coming with global warming, big risk. Is that really an issue if we know that climate change has happened in the past and it still will happen in the future? So why should we worry about this, this global warming. And definitely, well, we see that this global warming is happening. Different measurement I wanted with this slideshow to show that definitely it's happening. Different measurements made in different places on the planet show that there is an increase of temperature, especially since the second half of the 21st century. We observe definitely a continuous increase of temperature. We kind of had a release happening right there, which indirectly is linked to the Second World War. Less human activity, less industrial activities in general led to a little bit less CO2 emissions, but then we had just over the last 70 years at this point kept increasing our temperature in itself. And we observed that, as we saw from the video at the beginning of the class, that our average temperature, which was below normal at the beginning of last century, now is just above average. So we are definitely increasing our temperature, and that has kept constant over the last 70 years. And in fact, if we look at that over the last 200 years with the Industrial Revolution, we have just a pretty clear trend of an increase in temperature happening. And so again, we could say, well, temperature has increased, has decreased over time. That's part of climate change. Okay, but if we look at this graph, which shows you from an ice core the last 500,000 years, we observe this is carbon dioxide, CO2. What we observe is increase and decrease of carbon dioxide, which indirectly is also showing you increase and decrease in temperature. Okay, we saw that carbon dioxide and temperature goes well all along. So we observe increase and decrease in temperature. But what happened is right now, the increase in CO2 is becoming out of control. We have not seen that happening in the past. Never the planet has been seeing an increase of CO2 that fast. And if I'm going back to the slide, to a level that has not been observed over the last 1 million years. It's the first time ever in 1 million years, at least, then the CO2 level is reaching this amount and it's keeping increasing. So definitely the global warming is a big issue in the fact that we are reaching concentration of CO2 that goes higher than what we observed in the past, in the recent past, and the rate, the speed of this change happened very, very quickly. Okay. With that, I'll stop here and I will keep, I think I had a couple of more slides, but I will keep them for Thursday, and we will end up the class on climate change. I just wanted quickly to end up with the exit questions of Mentimeter to end up the class, and then answering any question if you do have some. I'll give 1 minute for everyone to connect. Okay. And in the same time, I'm reading at Dylan's question about the possible Earth going to another snowball sometime in the far future. I'm not sure if Dylan, you're thinking about the movie or TV shows called Snowpiercer. That definitely kind of go with this idea. But at least I would say naturally the planet naturally was supposed to be going into a glacial period again, meaning cooling down in temperature, but not to the extreme of being a snowball anymore. That was not being part of the plan in some way for the natural thing. And I would say beside human action, there is nothing that normally should lead to a snowball Earth anymore. Okay. All right, let's play the game. Come on. So a couple of questions. All right, that's a climate description. Good. Some of you fell into the trap. Careful on that. Question 2. That was true. Ah, interesting that you mostly fell into the wrong answer. That's definitely thanks to greenhouse gases that we are above freezing condition. Question 3. So this one is more like in terms of the most appropriate one. Definitely written records. They don't go that far in the history of human and the history of Earth to provide us data about the past climate. That was false. Yeah, we observed time that the dinosaur, for example, then the temperature was warmer than today. And last question. Oh, I forgot over the last 8,000 years. I forgot the year, the word years. Okay, this one is definitely true. Okay, well, that was part of our last slide. Okay, so let's see quickly at the leaderboard. Oh, we had the first 3 ones, very, very narrow. Good job, guys. And final question, just to let us know how was the class. Okay, and with that, that's the end of the session of the day. Okay, if you have any question, let me know. Otherwise, I wish you a good rest of your day, and I'll see you on Thursday for our last lecture.
Thank you,
Professor,
Professor.
have a good day.
Have a good day.
Bye.
Thank you.
You're welcome. Have a good rest of your day.